Let us solve a few problems to better understand the computation of specific probabilities given the probability distribution function. And we will also look at the approximation of discrete distribution as continuous distribution as well. So let's start with the first problem, which has three subproblems. An adult has on average 5 liters of blood. Assume the variable is normally distributed and has a standard deviation of 0.3. Find the following probabilities. So let us see what is our random variable. The random variable x here is quantity of blood in an adult, right? And we know that the expected value of this is 5 liters and the standard deviation of x is 0.3 liters. So first we want to find the percentage of adults who have less than 5.5 liters of blood in their system. So let's look at the value of x is less than equal to 5.5 is our variable value of interest, is the event of interest. So we need to determine probability of x less than equal to 5.5. Now we know that it follows the normal distribution. Let me show it to you diagrammatically. So let's say the mean is 5 liters and the standard deviation is 0.3. So let's make it 0.3. And we are interested in less than equal to 5.5. So we are interested in this value at 5.5. So we want to determine this value. Of course, the app has already given us the value less than 5.5. We can kind of consider less than equal to 5.5 as same, because in a continuous distribution the value of p is equal to 5.5 is 0, or p is equal to any value is 0. So how will we calculate it? Is equal to norm dot test, where the value is 5.5, mean is 5, standard deviation is 0.3, and we need to calculate the cumulative area under the curve, and that is 0.95221. So 95.221% people have 5.5 or less liters of blood in their body. Now our variable of interest is x greater than equal to 4.8. So now the problem is the norm dist function only calculates from the left hand side to the value x. So how will we determine it? So what we're going to do is we need to change this 5.5 to 4.8, but we are not interested in less than equal to, we are interested in the upper tail, the area after this. So how do we calculate this? We calculate this by calculating the area until this point, and we know the total area in any distribution is equal to 1. So we will subtract this white area from 1 to get this value. So probability of x greater than equal to 4.8 is same as 1 minus probability of x less than equal to 4.8. All right. is equal to 1 minus norm dot test 0.8 mean comma standard deviation comma cumulative, which is 74.75. We can similarly calculate this also, is equal to norm dot dist 4.8 comma 5 comma 0.3 comma true. So of course the sum total of these two will be equal to 1. Now the third scenario is where we want x to be greater than equal to 4.8 and less than equal to 5.5. So pictorially, how do we represent it? We want to have the middle value wherein the lower bound is 4.8 and the upper bound is 5.5. So we want to calculate this, which will of course turn out to be 0.7. So what we do here is we calculate the value until 5.5 and subtract the value until 4.8 to get this value. So probability of x being between 5.5 is same as probability of 0.5 minus probability of x. I need to put it other way around. 0.8 right, and less than equal to 4. So when we take the difference between these two values, we get the answer. So what is the probability of less than equal to 5.5? 0.95221 minus what is the probability of less than equal to 4.8 is 0.2528, which is 0.69972. Actually, I should have represented this so this is correct. So what I've calculated here is not this value, but I have calculated here is probability of x less than equal to 4.8. all right, so this is same as this, so these two are same, and so computationally we have used this. I can move this whole thing down. So we know the way the formula works and what we really want. We can do the computation as per the formula and apply the basic algebra and the symmetricity of the normal curve to determine the different probabilities for different types of outcomes. Now let us also solve for a binomial distribution. So let us say we have 10% of New Brunswickers allergic to ragweed. A random sample of 200 people is selected. Find the probability that 10 or more people will be allergic to ragweed. So what is our random variable? Number of New Brunswickers allergic to ragweed. All right, and we know that 10% of the people are allergic, 0.10, and our sample is n is equal to 200, and and we are looking for a probability of 10 or more, so R here is 10. So now we want to calculate the binomial probability of it. So let's kind of solve it using binomial, and then we will solve it using normal approximation to binomial. So let's switch to binomial. We are talking about n of 200 and p of 0.1, and we want to calculate probability of 10 or more. So we are looking at upper tail, and the value of A is 10, and we are looking at greater than equal to 10, right? So it's almost like 0.99, so 99.6% will be greater than or equal to 10. So we are looking at x greater than equal to 10. How do we calculate it? So we want to calculate probability of x greater than equal to 10. Now our distribution function, the normal distribution function, does not give us the values from the given point until the end, right? But it does give us the value from the probability of x less than 10, right? Or we can say less than equal to 9, because there are no values between 9 and 10, so both of them are equal, right? So we know this value, so this will be 1 minus probability of x less than equal to 9. Now what is the probability of p x less than equal to 9, which will be equal to binom distribution, number of success, we are looking at 10, and how many trials? 200 trials. What is the probability of success? 0.1, and we want to calculate the cumulative value. Oh, this should be comma. Now we cannot use 10 because that will include the 10 in the lower side. So I will say minus 1, right? So I'm looking at 9 successes cumulative among 200 trials, with each trial having a success rate of 0.1, and cumulatively we are going to calculate it. So we get 0.003529. So probability of x greater than equal to 10 will be 1 minus 0.003529 is equal to 1 minus, which is 99.6471%. Now we can solve the same problem using the normal approximation as well. So let's see how do we do it and how do we apply the continuity correction. So what we need to know expected value of x and standard deviation of x to do so. So expected value of x is given by np, and standard deviation is given by square root of np cube, or np1 minus P. So that's how we compute it. So let's check is equal to n star 0.1 point, that is 20, and is equal to square root of n times P times 1 minus P. So that is 4.242641. Alright. Now to apply a binomial approximation, we need to check for certain preconditions, which says NP should be greater than equal to 5 and n times 1 minus p should also be greater than equal to 5. If this condition is met, we can apply the normal approximation. So NP, we have calculated it, is n times p, and NQ, or n times 1 minus p. So yes, we can apply the normal distribution approximation to this binomial distribution. So now we need to know the probability of x greater than equal to 10, right? Now we will apply the continuity correction, and that will make it probability of x greater than equal to 9.5. That's the 0.5 correction, because there is no value between 9 and 10, so probability of 10 inclusive will be considered from 9.5. So now I can apply is equal to norm dot dist. Oh, I haven't indicated that 9.5 anything anywhere specifically, so 0.5 comma, what is the mean? Mean is 20, standard deviation is 4.242641, and we want to calculate the cumulative. So this will be this whole thing need to be subtracted from 1, because this is actually giving us the probability of x less than equal to 9.5. So I will calculate 1 minus cumulative probability until 9.5. So complement of this will be greater than equal to 9.5. When I calculate, I get a probability value of 99.336%. So let's see if I can approximately show it using the normal. The expected value is 20, and the standard deviation is 4.24. I do not know if it will allow me, so let's kind of keep it at 4.2, and I'm looking at the upper tail for the value 9.5. I'm not able to get exact 9.5, but since I'm kind of taking 4.2 instead of 4.242, so we see that it's kind of comes close to 0.993, which is same value which we have calculated here. So this is how we apply the continuity correction when we use a continuous probability distribution to a discrete probability distribution.